All right, everybody, this is our last lesson of the year. Yay! Don't forget to take the quiz on this stuff that will be due on Wednesday of next week or this Wednesday, depending on whenever you're listening to this lesson. So today we're going to talk about lesson 3, and it's permutations, and combinations. Well, the good thing is we're not going to talk really much about probability with them. That really would take another lesson. We don't have time for another lesson. So we're just going to talk about permutation and combinations. You're going to talk more about this in Algebra 2, and you'll talk more about it in pre-calculus as well. So it's good to get a good foundation down on what it means. Before we get to permutation or combination, we actually have to discuss the fundamental counting theorem. That is actually what permutations are based upon. So fundamental counting theorem, let's consider this story. So it's 6 a.m., you're groggy, but you have to pick out an outfit to wear. Lucky for you, you did not do laundry and you only have 3 pairs of pants, 2 t-shirts, and 2 pairs of socks to choose from. How many outfits can you actually put together? We're actually going to draw the sample space on this one. So we're going to draw every single possible outfit you could possibly wear. Remember, this is called sample space. This is our sample space. So let's say, okay, we have 3 pairs of pants. Let's go ahead and draw those. So you pick your pants first. Ooh, you have a weird leg on that side. Maybe you have some skinny jeans on this one. Oh, those are really skinny jeans. You once again have a weird other leg. That's okay. And maybe you have some bell bottoms. I think bell bottoms look something like this. There, your leg's better on that one. All right, so you pick out a pair of pants. You have 3 to choose from. Well, if you pick pants 1 with the weird leg over there, you would now have 2 shirts to choose from. And let's just say they both match. So we have 2 shirts. That's a nice shirt. And we have another shirt here. Oh, that went away from me. So we got a shirt here. Perfect drawing abilities. Maybe this one is a bat, it looks like. But let's say it's a striped shirt. Okay, so if I choose that pair of pants, I have 2 shirts to choose from. Well, if I choose my skinny pair of pants, I also have the same 2 shirts I can match with it because I only have 2 shirts to choose from. So that pant option also has these 2 shirts to choose from. Ooh, that's a good shirt. That's a money shirt until I drew stripes on it, then it kind of looked weird. Anyway, and if I choose bell bottoms, I also have 2 shirts to choose from. Move them over a little bit. There we go. One more shirt I have to draw. There we go. Nailed it. Ooh, it's almost an elephant. They all kind of look like elephants. Anyway, so no matter what pair of pants I have, I now have 2 shirts to choose from. Well, let's say I selected my shirt and I chose this pair of pants. I chose this shirt. Now I have to choose socks. Oh, socks. These are going to be great. So we have sock number 1 and sock number 2. Say it's a polka dot socks. Never mind. I decided to choose the striped shirt. Once again, I would have 2 pairs of socks to match with that. Nope, that's not my dotted one. The other one's going to be the dotted one. And we'd have the same choice for all of these shirts. I'm just going to go sock 1, sock 2. I think I did enough drawing. Feel free to draw your own. Sock 2. Oh boy. Sock 1, sock 2, sock 1, sock 2. Now, this is called sample space, but more specifically, this is known as a tree diagram. You're drawing every single branch, i.e. tree, of your choices. If I chose pants 1, I have 2 shirts to choose from. I have 2 socks to match with each of those shirts. So in effect, I drew every possible outfit I could possibly put together. Well, if we kind of look at the branches, each branch leads to one solution. So if I look at this, that's one outfit I could wear. Another outfit I could wear is going all the way down to the sock. That's another outfit I could wear. Here I could wear this outfit here. And this would be another outfit with the polka dot socks. So we're going to notice at the end of each branch is actually a different outfit. So with sock number 1, so if I'm looking here, that's one possible outfit. That's my first outfit. The one ending with the polka dot is another outfit. Ending with this sock is my third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. There are 12 different outfits I can put together. There are 12 outfits. But what I want to focus on is we had 3 pairs of pants. We had 2 shirts. That's not how you spell shirts. That's a better way to spell shirts. And we had 2 socks. Now, you must be thinking to yourself, we're not going to draw a tree diagram every single time, because if I added a hat to this, or a necklace, or we had more shirts, it would take an infinite amount of time to draw these. 12 is enough. So let's look at that 3, that 2, and that 2. There must be some way that these 3 things get together and come out to 12 with just the numbers. Well, if I added 3 plus 2 plus 2, that would give me 7. Let's go back. Let's think of multiplication. What's 3 times 2? That's 6 times 2 equals, oh boy, that equals 12. I think we're onto something, and that's going to work for every one of these things that work like this. So if we read right below it, or if you cheated and went ahead, it says, fundamental counting principle. If you can choose one item from group M, that's pants, and a second item from group N, that's shirts, then the total number of the 2 item choices is M times N. We just threw another one in. All right, let's call it S. We have a group S for socks. So it would just be M times N times S. Pants, shirts, socks, multiply it, and you come up with how many you have. You do not need to draw this tree diagram every single time. Good news is you can always draw that tree diagram. If you have plenty of time and you love drawing, feel free to draw every one of these out, but no, it's a long, long time, especially some of these have like 1,000 possibilities. You have to draw 1,000 different items, possibly more. So probably not a good idea, but you do you, I guess. All right. That's our fundamental counting principle. Let's use this in some practice. So it says an ice cream shop offers 8 different flavors with 9 different toppings, and the ice cream can be served in a cup, a waffle cone, or on a chocolate cone. Determine the number of possible choices. All right, so I go up there and I pick a flavor. We're going to say you only can pick one flavor, you only can pick one topping, you can only pick one item to put it in. So we're going to go with that, make our life a little easier. All right. So I need to pick a flavor. So we have 8 different flavors to choose from. That's our group M. We have 9 different toppings. That'll be my group N. And we have 3 different places I can put it in. Let's call it our group S. So we have M times N times S. So we have 8 flavors. That's our first choice. We have 9 toppings. And we have 3 kind of, I don't know, serving items, dishes, holders, I don't know. Let's say 3 holders. Well, this sounds like we're picking one from each group. So if you're picking one from each group, all you have to do is multiply it. 8 times 9 times 3 is going to be, you have 216 different ways to get that ice cream into a cup. That's a lot, considering it's only 8 flavors, 9 toppings, and 3 choices of serving dishes. 216 different ways. So these can add up really, really quick. All right, James needs a 4-digit password for his computer. The password can contain any number, no repeating. So no repeating numbers. So you can't have like 999. 9. Oh, there's 4 of them. All right. So how many possible passwords are there? So we need a 4-digit password. So let's go with that. 1, 2, 3, 4. This is my first number. This is my second number, my third number, and my fourth number. All right, it could be any number except you can't reuse a number. Okay, so my very first number, so we can include 0 in this group. We can choose 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That would be a single digit I can put in that one thing. Well, there's 10 numbers I can pick. I can pick 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That is 10 different numbers I can choose from. Well, my second one is dependent on that first number. So it kind of goes back to yesterday's lesson of dependent. Because I can't repeat any numbers, I now only have 9 to choose from. Well, my third, so I picked a number for the first one, I picked a number for the second one. There's only 8 numbers left for the third, and there's only 7 numbers left for that fourth one. Well, we're picking a number from each of these groups, so all I have to do is multiply those together, and we're going to come up with, there's 5,040 different ways to do that without a repeating digit. Note, if I was allowed to have repeating digits, it would be 10 times 10 times 10 times 10. Maybe I missed one. 10 times 10 times 10 times 10. Yeah. All right, this is if there's no repeating though. I want to notice this pattern though, 10, 9, 8, 7. That's actually going to lead us to our next big item, and that is called a factorial. A factorial is the product of the integers of all of the positive integers less than that integer. Whew. Factorials must go all the way down to 1. So for example, and I want to note our notation is an exclamation point. Your calculators all have that exclamation point on. It's probably a good idea for you to look up where that exclamation point is on your calculator and how to use it, because these get really big really fast. Consider if I have 22 factorial, that'd be 22 times 21 times 20 times 19, and you don't want to have to type all that into your calculator. So our example is 7 factorial. 7 factorial is something you could type in. I do strongly suggest you find out where your factorial button is on your calculator. You're looking for that exclamation point. YouTube's a great way. Just type in what calculator have and where is that button, and usually you can find a video or at least a picture on the internet. All right, so 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. Oddly enough, it's the exact same thing as 10 times 9 times 8 times 7. Coincidence? Maybe. All right, I do want to point out one really important fact that people forget about. 0 factorial equals 1. And that's because all factorials count down to 1. So 0 factorial equals 1. 1 factorial also equals 1. And why that is you really have to get into what factorials mean. Factorials are basically how many different ways there are to arrange a number. So like number 7, how many different ways are there to arrange 7 items? Well, there would be 5,040 different ways to arrange those items. Well, how many different ways are there to arrange 0 items? Well, there's one way. You don't, but it still counts as a way. So that's why 0 factorial equals 1. And factorials are primarily used for permutations and all this stuff, and that's why they're dealing with how many different ways there are to arrange stuff. That really is what a factorial is. All right, let's go. Just remember that fact. 0 factorial equals 1. It's one way to arrange 0. So if there are 13 players on a softball team, I wish we had a softball team this year, next year. All right, how many different ways can the coach assign the first 3 batters in the lineup? All right, so we have 13 players. How many different ways are there to arrange those into our first batter, second batter, and third batter? Well, starting off, we have 13 players that I could have as our leadoff batter. Awesome. Well, now we have that player picked. So our second batter I no longer have 13 options. I now only have 12 options. Well, for my third batter, I'm down to 11 players left for that third batter. What I want to point out is this is a factorial. It's 13 times 12 times 11. However, it's a permutation, or not a permutation, well, we'll get to it. It is a permutation. However, it's a factorial that stops at a very specific spot. I'm basically doing, I want a factorial, but only the first 3 multiplications. I'm going to stop after that. So that's just going to equal 13 times 12 times 11, which is 17, 16. Why this is important is because we're going to get to permutations next. Permutations are a way for me to go, I want a factorial, but I want it to stop after 3 multiplications. Or I want it to stop after 4. I want to do 13 times 12 times 11 times 10. And I would like to be able to tell my calculator to do that math for me without having to do all the big multiplications. And that gets us to a permutation. The big thing you need to recognize about a permutation is this right here. Order matters. Because we're going to talk about combinations in a second, and combinations are where order does not matter. So in these problems, you have to decide, does order matter? Is there a first, second, third, where it's different if you're first, second, or third? Or does it not matter? So let's go through our permutation where order matters, then we'll go through some combination problems where order doesn't matter so you can see the difference. All right, so as soon as we do permutation, in other words, order matters, we can use this permutation formula. Now, permutation can be shorthanded like this. It can be shorthanded like this. But in either case, it's always going to be that n value on top and that r value and n value down here. So we're going to have n factorial over n minus r factorial. I do want to point something out that's really important with permutations. When doing permutations, that n is always going to be the bigger number. So if you're ever confused on which one's your n and which one's your r, that is always your bigger number, and your bigger number always goes on top. That will be the same for combination as well. So your bigger number always comes first and always goes on top. Now, what do we mean by this n and r? Well, this n and r stand for n objects taken r at a time. So let's go back to our softball question. We're going to add another batter into it. It says, how many different arrangements can there be for the first 4 positions of, we changed it to a baseball team, baseball batting order if there's 13 players? Well, if I was using the fundamental counting theorem, I would just go, okay, there's 13 for the first, 12 for the second, 11 for the third, and we have 10 players to choose from for that 4th batter spot, which is going to equal 17,160 different ways. That's a lot of ways just to organize 4 batters. Well, this is a permutation problem. Order matters, and I'm picking 4 items out of 13. So what we can do is we can set this up as a permutation problem because order does matter, and we're picking 4 things out of a group of things. So it's you're basically picking. It's kind of like the fundamental counting theorem where you're picking a certain number from a group. Well, in this case, we have 13 total items I can choose from. And I want to fill 4 spots. Another way to write that is 13 choose 4 or pick 4. Well, the permutation formula is 13 factorial over 13 minus 4 factorial. Well, 13 minus 4 factorial is just 9 factorial. Well, 13 factorial would be 13 times 12 times 11 times 10. This is the only time I'm going to write it all out. Times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All over 9 factorial, which would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Whew. Like I said, that's the last time I'm going to write it all out. Because what I'm going to recognize is the fact that 9 factorial cancels out with that 9 kind of factorial. So what I kind of want you to start thinking about is, I'm going to write this underneath. Don't think of this as being 13, just strictly 13 factorial. What I kind of want you to start thinking about is that top is really 13 times 12 times 11 times 10 times 9 all the way down to 1. So really it's 13 times 12 times 11 times 10 times 9 factorial. You can rewrite 13 factorial in this terms, which allows you to look at the bottom as being 9 factorial. You can just cross out your factorials without writing it all out. Whatever the case, we're just left with 13 times 12 times 11 times 10, which is your 17,160. So you get the exact same answer. So in other words, a permutation of 13 pick 4 is just telling you what are the first 4 numbers of 13 factorial. Let's move down and do another one. All right, the next one says a software company is placing the 6 out of 10. Hang on. All right, a software company is placing the best 6 out of 10 possible applications on display in a specific order. Note it says it wants it in a specific order. Order matters, so that's going to make it a permutation. Remember, to be a permutation, order has to matter. How many different ways can the applications be arranged? Okay, so in short, we have 10 total, and we are picking 6 of them. Permutation, 10 pick 6. That's 10 factorial. Remember, our bigger number goes on top, and then we have bigger minus smaller on bottom factorial. I want to think about 10 minus 6 is actually 4 factorial. So what I want to do here is I want to start thinking of, okay, it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm actually going to end right at that 4. Because 4 factorial is 4 times 3, so I can actually end at any point and put a factorial symbol on it. And I'm doing it right there because on the bottom it's just 4 factorial, which means these cancel out. So in my calculator, all I have to do is 10 times 9 times 8 times 7 times 6 times 5, which is going to equal, looks like we have 151,200. If you know where your factorial button is on your calculator, you can also just do 10 factorial divided by 4 factorial. Your calculator will do all of that extra math for you. All right, that's permutation. Permutation order matters. Combination. Combination order does not matter. So if order doesn't matter, we have to use a combination. Our combination formula, it's still n objects taken r times. However, our new formula, we can also still do the Cn comma r. I am going to note that once again, n is your bigger number. If you ever get lost, and your bigger number always goes on top. And the cool thing about our combination formula, it's very similar to our permutation. The only difference is we multiply our denominator by r. Big minus small times small. All right, there are 15 I can't even read it. Let's get rid of that for just a second. All right, there are 15 applicants for 4 systems engineer positions. What I want to notice is they didn't rank the engineer positions. They're all the exact same position. So if I'm an applicant, I don't care which one I get. So I don't care if I'm the first one picked, second one picked, third one picked, or fourth one picked. As long as I get picked, it's all the same to me. So order does not matter. Order does not matter. I just want to get picked. So this is going to be a combination problem. So we have 15 total applicants, and we are choosing 4 of them. Well, the formula is take your big number, put it on top, put a factorial after it. Do big minus small times small. Here's where we can get a little creative with crossing numbers out as well. So we're doing our 15 minus 4, which is going to give me that 11 factorial. All right, what I'm going to do is 11 factorial is our biggest factorial. So what I'm going to do is I'm actually going to go, okay, 15 times 14 times 13 times 12 times 11, and I'm going to tack a factorial on there. because we have 11 factorial in the denominator. I also have 4 factorial, which is actually 4 times 3 times 2 times 1. What I'm going to do is I'm going to do some eliminating. 11 factorial. I can actually go further. So let's say I'm on a test and I don't have my calculator and I don't want to do this much calculations. What we can do here is I can actually look at this and go, okay, what's 4 times 3? Well, 4 times 3 is equal to 12. So I can actually cancel those out. I could go a little further. I'm not going to. I'm just going to hint at it. I'm going to do it and then I'm going to undo it. This is 2. I could cross that out with this 14 and make that a 7 to make my life even easier. I'm not going to because I'm just going to say I got my calculator. Let's just get that far. Let's do 15 times 14 times 13 and divide that by 2. So we have 15 times 14 times 13, and we're going to divide by 2, and that's just going to equal 1365. If any of those multiplications are off, please let me know. I just kind of plugged them in the calculator. I just got them off to the side. I'm not doing them as we're doing them to double check. So there's always a chance I might have pushed a button wrong. So don't try it 106 times. If you try it like twice and you still get the wrong answer, just email me or talk to me in class in case some of these are off. All right, final one. Bobby's manager asked him to make a display using 5 different styles of shirts from 8 available styles. How many ways can Bobby choose the t-shirt? So he's got 8 styles, and he just needs to pick out 5 of them. It doesn't matter what order he picks them out in. He just needs 5 of those items. So once again, order does not matter, which is going to make it a combination problem. So this will be a combination since order doesn't matter. He just needs to pick 5. Combination is we have 8 possible. We are choosing 5 of them. Another way to write that is 8 choose 5. Formula is big on top, big minus small on bottom, and the difference is for combination we multiply by small. All right, we're going to have 8 factorial on top. Actually, let me do a little bit of math down here. So if I look at this, 8 minus 5 is 3 factorial. The big number I'm looking at is this 5 factorial. Because when I do my 8 factorial, I have 8 times 7 times 6 times 5 factorial. Now with the 3 factorial, it would be 3 times 2 times 1 times, and we have that 5 factorial underlined over here. Except the cool thing is this 5 factorial would cancel out with that. I'm also going to notice, hey, what's 3 times 2? Well, that equals 6, so I can cancel out this 6. So I didn't even need my calculator on this one. I just needed to do 8 times 7, which equals 56. All right, that's all I have for you. I do want to note there's not a ton of room for those first 9. So either write really small or do it on a separate sheet of paper. Also, for some of these, you're really going to want your calculator. If you look at number 10, number 10 has 190, choose 3. You probably don't want to write out 190 times 189 times 188, so on and so forth. You need to know where that button is on your calculator. I think that's the only one with really big numbers. The rest you could do on your calculator without knowing that button, but you really need to know that button for that one. All right, everyone, good luck on this. Remember, the only thing you have left after this is to take that quiz. The quiz is due Wednesday. Good luck. I will see you hopefully between this video and when you take the quiz. All right, everyone, see ya.